Let's look at an example of the Bernoulli Principle or Bernoulli's equation in action with the Bernoulli Principle for a leaky water tank. So it says, in the Old West, a desperado fires a bullet into an open water tank, creating a hole a distance h below the water surface. What is the speed v of the water exiting the tank? All right. So this is a really cool problem in that it highlights a lot of potential assumptions that can be made. And it ends up having a very simple solution. So it's a classic problem. You see it in most physics textbooks in some form or another. So let's take a look, and I will stop sharing my screen so we can see the whiteboard a little more clearly. All right, so we have our water tank, and the desperado fires a bullet, and so the water is leaking out of the tank, and they tell us that there's this height h between the top of the water level and where the bullet hole is of where the water is coming out. And what we want to find is the speed of the water as it's leaving the tank. All right, so right in here, I draw my tangent line. That would be my want. Now, what we need to fill in is what we know. Okay, and so they give us this height h. So that's something. It's in terms of h. It's not a number, but we know we can solve in terms of it. What else do we know? I want you to pause for a moment and reflect on if there's anything else you could think of to write down. Right, I'm hoping you did that. So another thing we can mention is this is water, right? This is a water tank. And so that tells us that it's water. And why do we care that it's water? Well, that gives us the density, right? We know the density of water is 1,000 kilograms per cubic meter. And I'm going to assume it's fresh water because people don't usually drink salt water. So that's one thing we know. Another thing that the problem mentions is that it's an open air tank. It's an open water tank. So that gives us a key detail. If we pay attention to the top of the tank, this is open. Why do we care that it's open? Well, if it's open, that tells us about the pressure at that point. Since this is open and we haven't heard anything otherwise, that's going to have to be at atmospheric pressure. So that's a really good thing to notice too. All right, well, this is a pretty good start. So let's see, what tools might we want to use? Well, it tells us this is the Bernoulli principle. So that tells me probably want to use Bernoulli's equation. So the pressure at one point plus the kinetic energy density, 1/2 rho v1 squared plus rho gy1 is equal to all these same quantities with a 2. So pressure 2 plus 1/2 rho v2 squared plus rho gy2. All right. Now another equation that I want to bring up, because anytime we have fluids moving, we want to think of it, is our continuity equation. So our continuity equation, I'll also list over here, the area, cross-sectional area at one point times the speed at that point is equal to the cross-sectional area at some other point times the speed at that point. And that's the quickest way to find out how fast the fluid is moving. Now for both of these, we want to identify a point 1 and a point 2. We have to choose two particular places in our fluid's motion. We're trying to solve for the speed as it exits, so that seems like a good point to label, say, 2. right? Like it's the second point. So where the water is leaving is point 2. Where do we want to put point 1? Well, since they give us this height to the top of the water that's an open water tank, that's going to be a good place for us to consider as point 1. So the top of the water level. And I encourage you to draw this into your pictures just so you don't get confused later. It helps you keep everything more straight. All right. Well, let's take a look first at this continuity equation because we want to find the speed. And I said that the fastest way to do that is usually the continuity equation. So let's take a look. Well, we know we want to find V2. Do we have anything about the areas or the other velocity? Not quite. So this equation doesn't help us so much. But we could consider it, we could get the velocities in terms of V2. So I'm going to resolve this equation in terms of V1 for the others. So that would tell me then that V1 is equal to A2 divided by A1 times V2. And this is often what we would do on a problem if we were given these areas, is we would take these two areas, A2 over A1 times V2, and we would substitute this whole expression in for my velocity down here, right? A area over area times velocity, and that eliminates what our V1 unknown velocity. Now it's all of our velocities are written in terms of V2. So that's a good problem solving technique. But for this particular problem, we aren't going to do that because they don't give us numbers for the areas. This is where we're going to step back and see if we can make any assumptions about this. Well, we know that the hole at the bottom, which is our area 2, is created by a bullet. So how big is the cross-sectional area of a bullet? We're like yay big, right? It's pretty tiny. So maybe a centimeter diameter, maybe 2 if it's a really big bullet. So we could call it 2 centimeter diameter, radius of 1 centimeter. What about, what's the cross-sectional area of the top of the tank, right? Where the velocity is moving down. That area is a lot bigger, right? We could imagine the tank is maybe 2 meters across, a 1 meter diameter. Well, when you go to calculate these areas and use the radius squared, you'll find that area 2 is minuscule. The area of the bullet hole is tiny compared to the area of the tank. And as a result, V1 is absolutely tiny compared to V2. And that allows us to make the assumption that V1 is approximately equal to 0. You won't be doing this on most of the homework problems. They will just give you numbers, so you don't need to worry about that too much. But if you're at all uncomfortable with it, I encourage you to check it out with those numbers. Like, try out the numbers that we made up, right? That R2 is equal to 1 centimeter, R1 is equal to 1 meter. So we notice that R1 is 100 times bigger. When we square it, it becomes 10,000 times bigger. All right, so I'm going to leave that there with the assumption then that because of this conclusion above, we can set this as approximately equal to 0. Okay, so that's a nice simplification. We also noticed that at point 1, we said that the pressure is just equal to P sub 0. So that's another great thing that we can fill in. It's atmospheric pressure plus 0 plus rho g. And the density is the same. That's the density of water times g. I'm going to go ahead and to highlight things, I'm going to subtract my y2 over here. So if I subtract that whole term, rho g y2 over here, then the rho and the g are constant. So I can write this as y1 minus y2, where I've factored out the density and g after subtracting this over. There we go. And so that's the left side, and that is equal to pressure 2 on the right. Now, at point 2 on the right, do we know anything about the pressure here? This is another key assumption point. Well, we notice we're finding the pressure where the tank now has an opening, and the water is flowing out into atmosphere, into our atmospheric pressure. It's just going to be our standard rho naught atmospheric pressure. All right, and then plus this 1/2 rho V2 squared. Okay, it's only because we concluded that these pressures are the same that we can subtract them from this out. Right, we notice that we have 1 atmosphere of pressure on the left, 1 atmosphere of pressure on the right. They do cancel out. One thing to be careful of when you're solving problems with Bernoulli's equation, even if you know it's 1 atmosphere, if it doesn't cancel out, you need to write it in terms of your SI units, in terms of newtons per meter squared. Otherwise, your numbers will be very off. So make sure that anytime you're filling in the pressure, it's safest to do it in terms of SI units. So I could even demonstrate that here, right, that it's 1.01 times 10 to the 5th pascals. It's only because we have 1 over here, 1.01 times 10 to the 5th pascals, that we can subtract that away. And so then the pressures cancel out. They balance on both sides. And what we're left with after all of that, I'll move this down a little so we can see a bit more, is we have rho g y1 minus y2 is equal to 1/2 rho v2 squared. And now, only because there are no pressure terms, the densities will divide out. But that is doing division in order to eliminate those. It's not just a simple, I'm going to X them out because I want to, but we can divide by density. Oops, got my density symbol a little backwards there. There we go. We can also multiply both sides by 2 to cancel out the 1/2. The last thing we can note is this y1 minus y2. That's the relative heights of each of these points, right? Which, if we set the ground as 0, which we don't have to, we could call this y2. We could call that one y1. And we notice y1 minus y2 geometrically matches something already given to us in the problem. It's our height. The difference in height between our 2 points of interest. So this gives us a much simpler way of writing it, that we just have the 2 that we already multiplied out times g times h. And it's equal to v2 squared. So I'm just going to take the square root to get my speed of the water leaving it. Sorry, that square root got a little messy. Let's straighten that out. There we go. So V2 is equal to the square root of 2GH. Let's look at the neater version in the slides. So here in the slides, we see the same end result, that concluding that because of the continuity equation, because the area of the bullet hole is so much smaller than the area of the top of the tank, then the velocity of the water at the top of the tank is basically 0. It's much, much smaller than the water shooting out of the tank, so we don't need to consider it. And the pressure at the top of the water at the top of the tank, the pressure of the water coming out of the tank is both atmospheric pressure, so those will both cancel out. We can even set y equal to 0 at the point when the water is coming out, and y1 would just be equal to height, h then. That's another great way to approach solving this. And so then once we drop the initial velocity of the water at the top of the tank as it's falling at a very slow rate, we can get to our solution. V is equal to the square root of 2gh. And this is an equation we've seen before. I hope it's a little familiar to you. What does it look like? This looks like our potential energy becoming kinetic energy, right? mgh is equal to 1/2 mv squared. The m's cancel, we get that v is equal to square root of 2gh. And so this is a way to highlight the conservation of mechanical energy, that however much height the water started with tells you about how fast it's going when it's coming out. We're just converting our potential energy into kinetic energy. And indeed, if you had a truly ideal fluid, which we don't actually have, with no frictional losses, no viscosity, you could turn a pipe upward, that spout with an upward point, and the velocity would be such that the water could shoot up to exactly the height of the top of the water level because of the conservation of energy once again. So this highlights how we can use Bernoulli's principle along with the continuity equation and some of the important assumptions and calculations we'll need to do in order to solve it. If you have questions, please do reach out. I would love to chat further on all of this.